Okay. So, all right, so today I think we have the last set of reactions for alkenes that we'll talk about, and then on Monday and Tuesday of next week we're going to do problems, but on Monday we're going to talk, I don't think we'll make it here today, but we're going to talk about regio and stereoselectivity, which is something that you'll have to do on the next exam. Is not only will you have to write the major products of the reaction, but tell me whether the reaction is regio or stereoselective. So we have to go through what those terms are. If they were kind of confusing in the book, that's okay, because we'll go back and kind of define those, including characteristics of doing that. So that's what we'll do next week. And then we're going to jump into free radical halogenation when we get back from break for a couple days, and then we have the exam the Monday of the last week because it's in the syllabus, so I can do that. Right? There's no prohibition about giving an exam in the last week if it's in the syllabus, and it is. So and then we'll have some review for the final. So that's kind of where we're at. But first, so the last addition the second to last addition reaction. Again, I'll show you a mechanism to sort of help you with the stereochemistry, and this is what's called SIS hydroxylation. And so SIS hydroxylation means exactly what it says. I'm going to add two OH groups, 100% cis. And so there is no Markovnikov, anti-Markovnikov, when you're adding the same group to each of the two carbons in the double bond. So I'm adding two OH groups, neither Markovnikov or anti-Markovnikov, and this is going to be 100% cis. So there's actually two ways that I can do this. If I take, for instance, the alkene that we've been working with, the first way to add two OHs cis is to add a KMNO4 to it under basic conditions. And sometimes the conditions will vary here. Sometimes people will say KMNO4, you'll see cold versus warm. KMNO4 is an oxidizing reagent. So if we go back and remember about oxidizing and reduction from Wednesday,
Good morning.
Good morning, Sarah.
This is for you. It's Friday. I'll leave now.
Thank you. I did ask where she was at the beginning before class started. Okay, that's never happened before. One of these days she's going to be in a bad mood, and you're never going to be able to tell. Really? Have you seen her in a bad mood? Well, that's true. I guess I have to. Anyway, hey, see what you missed, people that didn't come to class today? All right, so we're going to add KMNO4. KMNO4 is an oxidizer, which means it adds oxygen to the molecule. And it's going to add oxygen in the form of the two OHs. Now, KMNO4 in the next reaction will actually cleave the double bond. So one of the ways to remember that this is KMNO4, and I will always give it to you with hydroxide. KMNO4 with hydroxide adds hydroxide. KMNO4 without hydroxide is going to do something else. Okay? So in this reaction then, what I'm going to end up doing is I'm going to add two OHs to the double bond, and I'm going to end up adding those cis. Although in this particular case, there's no way to tell that I added the OH cis. In a ring, you would clearly write 2 OH cis, and we'll do that. Okay, so this is one reagent that will add 2 OH cis. The other reagent that you can add, and they have similar mechanisms, which we'll do next, is to add osmium tetroxide, OSO4, and hydrogen peroxide. And that also will add 2 OHs, 100% cis. The cheaper method is to use CamNO4, because CamNO4, potassium permanganate is the purple reagent that you use maybe in general chem when you did iron titrations. It's dirt cheap. You can go, for instance, to the pet store and buy it for your aquarium, because it's one of the reagents that's used to clear cloudiness in an aquarium, because what it does is it goes through and it oxidizes all the organic stuff that is water insoluble, which makes it cloudy. It puts OH groups on it, which makes it water soluble, which then clears up your aquarium tank. And it's dilute enough where it's not going to kill anything living. So it's inexpensive. Osmium tetroxide is very expensive. Osmium is one of those metals that is in the transition metal part of the periodic table. It's very expensive, and I'll explain exactly why we need peroxide, because that's to make this reaction actually economically affordable. But both of these add 2 OHs, 100% cis. And the way that this mechanism works is that, for instance, if I took a ring and I add CamNO4 to it, or osmium tetroxide, what's going to happen is we're going to have the manganese double bonded to the oxygen so that the manganese looks like this. And actually, I'm going to switch where the O minus is, and I'm going to put the O minus over here just for the sake of argument. It doesn't really matter. But what's going to happen is the manganese dioxide, or the permanganate ion, is going to add to the double bond in a mechanism something like this. Take this pair of electrons and use it to form the carbon-oxygen bond. Take the double bond pair of electrons, use it to form the carbon-oxygen bond to the top carbon, and then take this pair of electrons and move it into the manganese. So this reaction fits our general chemistry description of oxidation, because the manganese atom is getting electrons, which means it's undergoing reduction, right? That's the GER part. So manganese is undergoing reduction. That means the other molecule is undergoing oxidation, which it is by gaining oxygens. So what we end up doing is we end up forming a 5-membered ring. And that 5-membered ring will look something like this. Now, this 5-membered ring is the reason why it's going to be cis addition, because a 5-membered ring is not big enough for one oxygen to add to the top of the ring and stretch all the way around to add the oxygen to the bottom side of the ring. That can't happen. And so in this 5-membered ring, the oxygens either have to add both to the top or both to the bottom, but the ring isn't big enough to add one top, one bottom. So we have to add cis. So if we're looking at shapes, our triangle means 100% trans. Our square means cis, and now our pentagon means cis. Okay. If you went to a 6-membered ring, that would probably be big enough to add something to the top and the bottom, but this is only a 5-membered ring. And this is an intermediate, actually. I mean, you could probably isolate this if you wanted to. Instead, what happens is the hydroxide, part of the permanganate hydroxide reagent, the hydroxide comes in, and the hydroxide removes the permanganate so that we end up with 2 OHs adding cis. And then the magnesium, or the manganese, ends up as MnO2, which is manganese dioxide. And we'll actually do a reaction with permanganate next semester in lab. We'll take the purple permanganate solution and we'll actually see it undergo reaction because you get a brown precipitate out of that product. And then what you do is, in lab, we actually have to filter out the manganese dioxide by using a C-light pad, like we did with the yeast cells. So this actually, well, I'll come back, and this can be used as a test for a double bond. Okay. So the critical part of this is, the reason I'm showing you this mechanism, and again, I'm not going to ask you to reproduce this mechanism on an exam, but I'm showing it to you so that if you get stuck, you can associate the permanganate with the 5-membered ring, which means it has to be cis. All right, so that's what happens with the permanganate. Does that kind of make sense? So for the osmium tetroxide, it's exactly the same thing. So for osmium tetroxide, bless you, I would have the osmium tetroxide look exactly like that. It looks very similar to the permanganate. And since it looks similar to the permanganate, I could move the pair of electrons, the double bond from the osmium to the oxygen to form a single bond, the double bond moving to form the carbon-oxygen bond, and the pair of electrons going into the osmium. So again, the osmium's gaining electrons, it's undergoing reduction, so that I'm going to still make the same 5-membered species with the osmium that I made with the permanganate. And so osmium must add 100% cis. Now the issue here is that for the osmium, because it's one of these transition metals, lanthanide metals, I couldn't do this reaction if I had to add 1 mole of osmium for every 1 mole of alkene. That would not be economically feasible. So what happens is that when we add the hydrogen peroxide, or when the hydrogen peroxide is in the mixture, first the hydrogen peroxide then strips the osmium off, leaving the 2 OHs behind, but then it reoxidizes the osmium to osmium tetroxide, so that basically this is a catalytic reaction, with the osmium tetroxide being a catalyst, so that osmium reacts and then gets reoxidized and then reacts with another mole of alkene, so that I can use a tiny bit of osmium to complete the reaction, and that's what's going to make it economically feasible. Otherwise, it wouldn't work. Okay. So either one of these reactions is fine to add the 2 OHs, but they both look very similar. They form a 5-membered ring. That's why it's that's why it's cis, 100% cis hydroxylation. Everybody okay with that? So both of those can be used to add two OHs, 100% cis. Now, KMNO4 can do something else. And that is that we can do what's called oxidative cleavage. Oxidative cleavage is going to, again, I mean, organic chemists aren't particularly creative. When we come up with names, we pretty much come up with names that tell you what it does. So SIS hydroxylation, 2OH is cis. Oxidative cleavage, I'm going to add oxygen to my molecule. I'm going to cleave the double bond. I'm going to break the molecule apart. So oxidative cleavage, for instance, if I take this double bond, I can cleave the double bond by using a couple of different sets of reagents. The reagents that will cleave this, the first one will be KMNO4, but not KMNO4 under base, KMNO4 under acidic conditions, or sometimes the books will say KMNO4 hot or warm. That's going to cleave the double bond. Okay. So in this case, I'm going to cleave this double bond, and over here, I'm just going to write the molecule, the two molecules without the double bond. So I'm going to erase the double bond. And I'm going to add oxygens to each of those two carbons. So what I'm going to end up doing, net result is, I'm going to end up replacing the C double bond with the two CO double bonds. So I'm going to cleave this molecule, and I'm going to add double bonds to the oxygen. Okay. Now, in order for us to look at these two products and decide whether we're finished or not, I need to explain the whole oxidative cycle for aldehydes, carboxylic acids, and primary alcohols. So, let's say that you have a primary alcohol. Why is this called a primary alcohol? Because the OH is attached to a primary carbon. Okay. Primary alcohols can first be oxidized to an aldehyde. And in this case, when I'm talking about oxidation, I'm talking about the loss of two hydrogens and the formation of the CO double bond. So that's where the oxidation term comes from. That aldehyde can be further oxidized up to a carboxylic acid. And that oxidation is the addition of an oxygen. So we'll talk about this more next semester, but we have the sequence of primary alcohol to aldehyde to carboxylic acid. And so that's our oxidation scheme. Most oxidizing reagents oxidize a primary alcohol all the way up to a carboxylic acid. And that includes reagents like hydrogen peroxide or KMNO4. So potassium permanganate and hydrogen peroxide will oxidize a primary alcohol all the way to a carboxylic acid, which means that they will oxidize an aldehyde also to a carboxylic acid. And that oxidation scheme is something that we need to know because when I do my cleavage, in this case, I cleave that molecule to form two aldehydes. Those aldehydes are going to be present in KMNO4. Those aldehydes are not going to stay as aldehydes because aldehydes get oxidized to a carboxylic acid under KMNO4 conditions. So when I make these two aldehydes, what happens is each one of them with the KMNO4 that's in solution are going to be oxidized up to carboxylic acids. So whenever I make an aldehyde by my first cleavage part, which is erase the double bond and put in two CO double bonds, if I have an aldehyde and I'm using KMNO4, that will be oxidized to the carboxylic acid. So the final answer to this reaction is I make two carboxylic acids. Okay. So we have to keep that in mind. So erase the double bond, replace with two CO double bonds, check if there's any aldehydes, they need to be oxidized to the carboxylic acid when I'm using KMNO4 and acid. So for instance, if I had that molecule and I said, let's go ahead and do oxidative cleavage by using KMNO4 and acid. The way I would write the product is I would again cleave the double bond. That means the molecule on the left becomes a ketone. The molecule on the right becomes an aldehyde. And that aldehyde, in the presence of the KMNO4, will be oxidized to the carboxylic acid. So that the final products of this reaction would be that ketone, which is acetone, and this carboxylic acid, which is the 2-carbon carboxylic acid, that's acetic acid. So oxidative cleavage is a two-step process. Cleave and then check for the aldehydes. Now ketones cannot be further oxidized. So when you make a ketone, it's done. So oftentimes you'll see, and you'll see in my notes, not the notes that I have that go with the video online, is I'll say KMNO4 and acid will make ketones and carboxylic acids. For some reactions, it might just make two ketones. For the others, it might make two carboxylic acids. Or you might get a mixture of ketone and carboxylic acid, depending on what your starting molecule is. But we cleave, convert to carbonyls, and then any aldehydes get oxidized up to carboxylic acids. Everybody with me so far that's here? If you're not here, you should be with me. Actually, you should be here first. It's like a podcast. We'll just leave them verbal shaming. What happens with the ring? With a ring, same thing, except when the ring breaks open, it's just a single molecule because those two parts are being held together by the rest of the ring. So if I said, okay, let's do KMNO4 oxidation on this double bond, I'm going to cleave the double bond of the cyclohexene. Right now, it's good enough if you just did this. If you just said, well, I'm going to convert those two carbons to carbonyls. The top carbonyl is a ketone, so nothing's going to happen to it. The bottom carbon is an aldehyde, so what's going to happen to it? It's going to be oxidized to the bottom carbon is going to be oxidized to a carboxylic acid. So initially, you can actually you don't have to manipulate the molecule and take it out of the ring structure. You just break the double bond and put in two C double bond O's. And if it's an aldehyde, it gets oxidized to a carboxylic acid. Now, you can do this on the next exam, leave it like that. I can figure that out. But if it's a multiple choice exam or it's somebody else's exam, they may take this molecule and they may stretch it out. So if you're going to stretch it out, at least beginning, my suggestion is we put numbers in here so we don't magically gain or lose a carbon along the way. So if you want to stretch this out, I have 7 carbons in this chain. So I would go 1, 2, 3, 4, 5, 6, 7. So I'm going to stretch it out so it's 7 carbons. Carbon 1 is a CH3. Carbon 2 is a C double bond O. The other one that has something is carbon 7. Carbon 7 is now a C double bond O OH. And then everything else is a CH2. So when you're taking this molecule and you're putting it in a straight line, or when you're stretching it out, my suggestion is when you first start doing that, put numbers to it so that you don't end up with an 8 carbon chain, or you don't end up with a 6 carbon chain, and you know where to put the groups. So that you know where to put the ketone, you know where to put the carboxylic acid. And if you really wanted to make this a difficult problem, we would go back to chapter 2 and you would get the names of this, right? Because then you'd have to go back and remember carboxylic acid has a higher priority than a ketone. The ketone's called an oxo group. So this would be a 2-oxoheptanoic acid would be its name. Right. I wouldn't do that on the next exam, but the final's coming, and also we need to review naming as we get ready for the final exam, which my suggestion is put exam 3 priority before the final exam. Then after exam 3, then put your priority on the final exam. But if you're overly ambitious and wanted to start going backwards, naming's going to be one of those things. So you can actually cleave a ring. And the other thing I will say is, because I know books like to do this, and Top Hat is one of them, that they'll give you this molecule and they say, what molecule did this come from? Whenever you see a single molecule, it had to come from a ring. And so if you're reconstructing, if they said, what alkene did this molecule come from? First of all, the fact that it's one molecule means that it's a ring. The 2 carbonyls were the 2 carbons that were bonded together. And remember, the carboxylic acid came from a CH, because it was oxidized with KMNO4. So they will have some of those problems, and if you get stuck, ask, and that's the way I'll suggest going about putting the molecule together. If it's two, you're going to join the two carbonyls together because that's how it was in the original molecule. Okay. So the idea of this ring, I'll just give you a sort of a practical example that I remember from a job interview from a long time ago, a job I obviously didn't get because I only take the jobs that are offered to me. And this was at DuPont. So DuPont's, one of the things that DuPont is known for is it was the chemical company that developed nylon. And that was a big deal to make parachutes and stuff out of in World War II, because otherwise, there aren't enough spiders to make silk to make parachutes, and also nylon's silk leg wear. So, the way you do that is you actually take an amine with like a 1, 2, 3, 4, 5, 1, 2, 3, 4. You take a 6-carbon chain, 6, with 2 amine groups on it, and you take a carboxylic acid with 1, 2, 3, 4, 5, 6. You take a carboxylic acid with 2 carboxylic acid groups on it. And what will happen is that the carboxylic acid group will react with the amine to make an amide functional group. And if you have 2 amines and 2 carboxylic acids, they just make this endless chain of what's called a polyamide. And a polyamide nowadays would be, it is a nylon, but there's many different types of nylon. Some plastic gears are made of nylon. They're made of polyamide. But, and you may have seen a demonstration. If not, you could look it up on YouTube, where they take a carboxylic acid and an amine and they mix them together, and then at the interface, that's where the nylon forms. So if you dip in a piece of copper, a copper wire hook, you can pull out this endless string of nylon. I think when I taught at OU, we did that in our GOB class, and then we had a prize for whoever could pull out the longest piece of nylon, which I believe was a yardstick. No other very good prize, but you can actually pull the long string of nylon out. Well, how does this relate to this molecule? I remember sitting in this guy's office at DuPont on a job interview at it was called the experimental station in Wilmington. And his group developed all of the fibers, the high performance fibers for things like bicycle racing. Okay, this was the late 80s, right? So we didn't have the performance wear that everybody wears nowadays, right? The performance wears were, $300 shirts for bicyclists. Nowadays, it's much cheaper than that. But the hollow fibers that allow the moisture to wick from the skin through the hollowness to the outside, his group developed all that stuff, which I thought was pretty impressive. Because I'm like, really? And then there are coatings on it. But one of the things that he said, it's still stuck with me to this day, a practical application of what we learn now is, he said, well, we make nylon. I said, yeah, I remember Wallace Carruthers did that. That was a report I had to do when my undergraduate chemistry program, I had to give a seminar on it. But yeah, I remember that. And he goes, well, where do we get the diacid? He goes, we just take this and we use something like KMNO4 because it's dirt cheap. And then when we cleave this double bond, we end up forming the diacid that has the 6-carbon chain. So he goes, that's in industrial chemistry, you need a really cheap starting material, and you need a really cheap reagent, and so that's how they did that. And so that's where they got their what's called adipic acid that they use to make their different nylons from. And if they wanted a 5-carbon chain, they started with a 5-carbon alkene. So I don't know, that's always stuck with me, like, oh yeah, I remember that from organic chemistry. It's like, oh, okay. There is a real world application to most everything we talk about. And if you're one of those students that needs that real world application, here it is. Students are saying, if it doesn't have an application, I don't remember it. I don't know how you function in life that way, but this is the relevance of that. Because it's all about making this stuff pennies per pound. You'll bankrupt the company if it costs $1 a pound to make. You'll stay in business if it's like 10 cents a pound. 10 cents might be too expensive too. So anyway, that's, like I said, his group came up with that, came up with all those things that we take for granted nowadays. Buy biking shirt, buy biking shirt at basically Target for $20. Back in the day, that would have been far more expensive. So, and that was the company, that's what they were known for, was coming up with those performance materials. So I thought, even if I didn't get the job, I got to meet the guy, and I thought that's pretty impressive that their group came up with all of that. Because most times in chemical companies, it's like, you don't know what they make, but that's what they made. Then, of course, they got to dye them, they got to put coatings on them. So even fabrics are complicated chemistry. In Cleveland, the paints are complicated industries. Right? What goes into a paint that Sherwin-Williams uses is super complicated. PPG for car paints, but there's a lot of chemistry and a lot of complication to it. But it basically boils down in some cases to these reactions that we're learning. So, if you're at Thanksgiving and they're like, and your family's like, why are you taking organic chemistry? Do you learn anything that's there? You can give them that. Practical organic chemistry. Okay. One last cleavage. What happens if the double bond is at the end of a chain? What happens then? Basically, same thing. Cleave the double bond. In this case, I would have an aldehyde, and then I'm going to have that aldehyde formed. Since this is going to be KMNO4, an acid still, this aldehyde is going to be oxidized up to the carboxylic acid, and this aldehyde is called formaldehyde. Right? If you've heard about formaldehyde, usually dead things are in formaldehyde because it's a preservative. Not in our biology department. I think they switched everything over to methanol years ago when we moved dead things from one building to another. I think they went to methanol, but formaldehyde is what can be used to preserve dead things. It's also used in plastics, sometimes in carpet fibers. So oftentimes you'll hear, oh, there's formaldehyde vapors in a building because they just put new carpet in. That's been trying to eliminate that, has been something that chemical and fiber makers have been trying to deal with for years. But what happens with the formaldehyde is it gets oxidized up to that carboxylic acid, which is called carbonic acid. Now, usually what I do is I say carbonic acid, I take my non-coffee beverage and I take a sip of it, and lukewarm coffee is not good, but normally that would be a carbonic acid beverage, a carbonated beverage, and so carbonic acid is not stable. It decomposes to carbon dioxide in water. So if you do cleavage on what's in this case called a terminal alkene, the alkene at the end of the chain, you would actually see fizzing in the reaction because you would see the carbonic acid being formed and then breaking up into CO2 and water. And that is actually can be used as a test for a double bond. Next semester in lab, we're going to start out for a number of weeks, probably too many weeks, is talking about spectroscopy. Because one of the issues, practical issues is, so somebody, let's say like Zaitsev. How did Zaitsev know that he always made the double, no, number one, how do you know he made a double bond? Number two, how do you know what double bond he made? How did he know the structure of the molecule? If Markovnikov had done what Markovnikov did, or is claimed to, or is given credit for, how would he know where the H and the Cl added? How do you know the structure of the molecule? If somebody walks up to me and hands me some stuff and say, "What is this?" It happens occasionally. It's happened with some companies where they're like, "This is our competitor's product. What is it?" So I'll figure it out. It's an ethical gray area. Every company does it. They want to know what their product. They want to know what their competitors' products are. Or in car paints, somebody makes a coating for the metal, and they won't tell them what's in it. And then I need to somehow get my paint to stick to that, but my company that I'm working with won't tell me what's in it, so I got to figure out what's in it in order to make it stick. There are some companies where nobody ever writes anything down. Even within the same company, I found that out recently with a guy who was helping us with one of our instruments. They don't do patents; they do trade secrets. So every time two groups talk together, they never write anything down because one group is trying to keep a secret from another group. It's all strange, but sometimes you got to figure out what the molecule is. So we'll learn about that with spectroscopy next semester. But before spectroscopy, we had a series of qualitative tests that we could do. And so let's say somebody gives me a molecule and I think I have a double bond. Well, I'm going to take that double bond, I'm going to add a drop of red bromine to it. And what happens? If it's double bond, the bromines add 100% trans, and the red color immediately disappears. Or I use KMNO4, and the purple color disappears and becomes a brown precipitate. That would tell me, hey, I have a double bond. It would also tell me I have a triple bond maybe, but it will help classify the molecule. Well, if I have a double bond and I say, I wonder if it's at the end of a chain, I might do this KMNO4 reaction and look for the fizz. And if I see the fizz, double bonds at the end of the chain. So there are all these different color tests that you can do to help identify a molecule. And this is one of the ones that's been used historically to determine, is my double bond at the end of the chain? If it is, KMNO4 acid will fizz. If it doesn't, then it's internal. Okay. With spectroscopy, I can figure that out in about, depending, 10, 15 minutes. If I have, $250,000 NMR. But if I have an NMR like I have, I can pretty much determine anything. And have for different things. So that's one of the techniques we'll talk about. Infrared we'll talk about. But this is the old qualitative tests. Okay? All right. So this is KMNO4 cleavage. What's in the textbook and what's more traditionally done is what's called ozonolysis. And ozonolysis has exactly the same products and characteristics of KMNO4 and acid, except one thing. So if I have my double bond, ozonolysis gives me the opportunity to decide for the aldehyde, do I want to keep it an aldehyde or do I want to oxidize it to a carboxylic acid? KMNO4 gives me no choice. KMNO4 is going to take any aldehydes that are made after cleavage and oxidize them to carboxylic acids. Ozonolysis I can choose. So ozone is O3. And I have two ways to do ozonolysis. I can do ozonolysis with H2O2, which would give me the same products, the same final products as KMNO4 and acid. So if I use ozonolysis and hydrogen peroxide, remember aldehydes will react with hydrogen peroxide just like KMNO4, and they'll be converted to carboxylic acids. So if I want to do the KMNO4 reaction, I can do ozonolysis with an oxidizing reagent like H2O2. But if I want to keep the aldehyde as the aldehyde, then I need to use a non-oxidizing pair. So ozone first, which will cleave the double bond, and then I would use something like R2S, which is basically a sulfur analog of an ether. So it has two alkyl groups on either side of the sulfur. In this case, the ketone is still going to be formed, but now the aldehyde will stay as the aldehyde and not be further oxidized. So ozonolysis gives us a little bit of choice in terms of what to do with the aldehyde. Do I want to oxidize it to an acid or do I want to keep it? And so ozonolysis is a little more flexible reagent to do this with. And so ozone, right? Ozone, is it good or is it bad? Well, ozone that's up there keeps the sun from frying us, right? It absorbs the UV light that comes in, particularly the UVC, which is sterilizing, skin burning, not just tanning, skin annihilating UV. Ozone that's at the ground is bad. So if you live in Cleveland or places where they have ozone action days, they'll come on the radio. Who listens to the radio anymore? But they'll come on and they'll say, today's an ozone action day. Don't fill up your car, don't be outside, don't mow your lawn, because what happens is that the emissions from the car, from the lawnmower, from the gasoline will at ground level form ozone, and that's bad. Because when it gets in your lungs, what happens? It probably starts to break down double bonds. Anything that's rubber will eventually break down because of ozone. That's why tires will eventually go bad, because they'll begin to break apart because the double bonds that are in the rubber are going to eventually become cleaved. It's not your tires just going to fall apart like, little granules of rubber that are over on the football field, because that's now the dirt of all AstroTurf fields is rubber tires. But eventually that ozone will attack things with double bonds. So atmospheric ozone, good. Ground level ozone, bad. Okay? Okay, I didn't get to free radical halogenation because we'll do that on Monday, and we'll do. So if you haven't worked through, like the last set of book problems that I've counted the grades for is, I think, chapter 6. So if you're up to date, you're okay, but I'll send an email over the weekend telling you the date at which I will record the grades. So if you're like, what are we at now? 5 chapters behind, you got a little work to do, okay? But if you have questions, put them on Piazza. I have a question about one of the problems from chapter 12, which I will do today, and I will put up. Otherwise, we'll do stereo and regioselectivity on Monday and Tuesday.